Part 4 of the Introduction to Amateur Astronomy lecture series is entitled Telescope Tutorial. So if you've joined us for parts 1, 2, and 3, you know this already, but for those of you that may be watching this lecture here for the first time, let me give you a little brief summary of what we've covered so far. So another name for the Introduction to Amateur Astronomy lecture series is Richard Bell's 4-step program to becoming a star-hopping star master or sky master. So that's a little on the wordy side, so you can see why I go with Introduction to Amateur Astronomy. So basically, in parts 1 through 3, we talked about how your first step as a budding amateur astronomer is not to buy a telescope. In fact, it's the worst thing you can do, because if you're very new to amateur astronomy and you know nothing about general astronomy or equipment, there's a very good chance you're going to buy the wrong telescope. You might have fun looking at the moon, planets, but eventually you'll get bored and you'll stick your telescope either in the closet or the weight room, and you'll try to sell it in a yard sale for $2 or something like that. So you'll take a huge loss on it. So obviously, do not buy a telescope first thing when you're getting going. The very first thing you should do is you should educate yourself. It's very good to learn Astronomy 101, the basic astronomy you learn in a first semester astronomy course. And you can also buy some books that are more relevant to amateur astronomy as well. All these books cover basic astronomy, but books like The Backyard Astronomer's Guide, Night Watch, and The Practical Astronomer, just to name a few, they cover amateur astronomy quite well as well. And then after you do a little bit of reading, a little bit of research, you want to learn the night sky. So for example, if you don't know that these two stars here in the Big Dipper point to Polaris, the North Star, then you're not ready yet. So if you're not familiar with this little star hopping trick, you are not ready to get a telescope yet. You need to learn the bright stars and major constellations of every season. And then before you jump to the telescope, you should do some observing with binoculars. Just get yourself a standard pair of 7x50 or 10x50 binoculars. They fill the gap between what your unaided eye can show you and what a telescope can show you. The naked eye can show you a lot of the sky. Telescopes show you a tiny portion of the sky. Binoculars fill that gap, and it's a great way to learn basic star hopping skills. So by all means, bring out your binoculars with you every clear night. They are a great tool just to quickly scan the night sky. And then after all that, you are ready to select the telescope. Do you have to use this exact method, or do you have to follow the exact steps to become an amateur astronomer? No. But if you want to avoid frustration, not waste any money, this is the way I recommend that you begin. So let's begin with telescopes. I mean, before we get into the telescopes themselves, we have to learn the terminology. Telescopes have their own lingo, like any other area. And learning the lingo also teaches you the basic and most important properties of a telescope. And by far, the most important property of a telescope is its aperture. So the aperture of a telescope is the diameter of either its objective lens or its primary mirror. So aperture relates directly with light gathering power, also known as light gathering capacity. And this is simply the ability of a telescope to collect light. And we often refer to telescopes as light buckets, because imagine if you have two buckets, one's kind of small and the other's big. And what if you get a big rainstorm? Which bucket is going to collect the most rain? And the answer is the bigger bucket, because it has a larger collecting area. So the same thing with telescopes, but instead of rain, hopefully they collect more photons than rain, because telescopes aren't terribly waterproof. Now, I do have a minor in mathematics, So I do like to throw a little math at folks from time to time, and there's really no better way to give you an example of this, another example, than mathematically. So let's do some very basic math. So here we have the area of a circle. And so if it's been a while since you had like a basic geometry course, the area of a circle is equal to pi times the radius squared. Now, we don't want to use the radius. We want to use the diameter, because that's how we express a telescope's main feature, is its diameter. So the radius is half the diameter. So that's why I have the diameter d divided by 2 squared. And so when we square this out, we get d squared divided by 4. So we have the area of a circle is equal to pi times the diameter squared divided by 4. All right, so let's say we want to compare the light gathering powers of two telescopes. So to do this, we just take the ratio of their diameters. So let's say we have telescope A and we have telescope B, and they have their various apertures. And so we divide these out. We have the area of telescope A, which we'll call the light gathering power of telescope A. You can call the variables whatever you want. And we have the area or light gathering power of telescope B. So the constants, the pi and the 4, cancel, and we're left with the diameter of telescope A divided by the diameter of telescope B squared. So let's do an example. So how much more light will a 10-meter telescope collect than a 10-inch or 1/4 meter telescope? So 10 meters is the aperture of the twin Keck telescopes in Hawaii. They each have a diameter of 10 meters or over 30 feet. So they are gigantic telescopes. And a 10-inch telescope, that's a very common size for an amateur astronomer. My first serious telescope as an amateur astronomer was a 10-inch Schmidt-Cassegrain. So let's compare these. Of course, the units have to be the same. So that's why I show you the aperture of a 10-inch in meters. So it's 1/4 of a meter. So we plug that in. 10 meters divided by 1/4 of a meter, or 0.25 meters. Basically, the 4 or 1/4 here comes to the top. So it's 4 times 10, which is 40. 40 squared is 1,600. So a 10-meter telescope collects 1,600 times more light than a 10-inch telescope. So that's why professional astronomers are always striving for the biggest telescopes they can build on top of mountaintops, because they want to collect as much light as you can. The more light you can collect, the brighter things are. Now, another important term related to aperture is angular resolution. Today, we're kind of familiar with resolutions in terms of cameras and TVs and stuff like that. But angular resolution is also known as resolving power, at least for telescopes. And this is quite simply the ability of a telescope to reveal fine detail. So aperture is also related to angular resolution. So the angular resolution, alpha, in arc seconds, is equal to 11.6 divided by the diameter in centimeters. You can express it in inches too, but then this number changes. So this little equation here is known as Dawes limit, D-A-W-E-S, and it's named after the English astronomer William Rudder, or W.R. Dawes. And it again describes the faintest detail that can be observed through a telescope under ideal seeing conditions. And so we use 11.6 when we express the diameter in centimeters, but you can change this out to 4.56 for inches. So if the diameter is in inches, again, you use 4.56. And people often wonder where the 11.6 or the 4.56 come from. And it wasn't derived. It's not like a derived constant, but it was determined empirically by actual field testing of many varied double stars. So it's kind of like an average of many observations of, binary star systems, or at least optical doubles. So that's where it comes from. But basically, this is just a quick way to help you calculate the angular resolution of your telescope if you know its aperture. So, for example, what is the angular resolution of a 10-inch, 25 centimeter, or 0.25 meter telescope? The metric system is so superior than the clunky system that we use here in the US. So obviously we want to have it in centimeters if we use 11.6, and we have 11.6 divided by 25 is 0.46 arc seconds. So remember, when you have the two little slashes like this, usually when people see this, they think it's inches. But in astronomy, when you see these two little hashes, that means arc seconds. And remember, 1 degree is equal to 60 arc minutes, which is equal to 3,600 arc seconds. That's a brief review from part 2 when we discussed angular resolution, because remember, we measure everything in the sky in angles. It's diameter, separation, even fields of view are measured in degrees or seconds or minutes of arc. Okay, so again, a 10-inch telescope cannot resolve details any finer than roughly half an arc second. Why can't it do better? How come you just can't use as much magnification as you want? And the answer is something known as the diffraction fringe. So the diffraction fringe is the blurred fringe that surrounds any image, and it's caused by the wave properties of light itself. So you may have heard, or of course you may have studied, that light has properties of a wave and a particle. Now, for our purposes, the particle stuff is not important. That's the realm of quantum mechanics, and of course we ain't going to touch any of that at all. I know some people might be disappointed, but there you go. So of course we're concerned with the wave properties of light with telescopes. And so this here is called an airy disk. And when people first started seeing this through telescopes, they thought they were resolving the diameters of stars. But it's something you can't avoid, but you can make it smaller, because obviously the larger the diameter of the telescope gets, the larger its aperture, the smaller this number gets. So that's the point that I'm getting to here, is not only do you get increased light gathering power with greater aperture, but you also get finer resolution. Now, can telescopes actually do this resolution with the 10-inch telescope? The answer is no, and we'll discuss this. But because of the airy disk, named after Sir George Biddle Airy, by the way, the 7th Astronomer Royal, no image detail smaller than the fringe can be seen. So this limits the resolution of a specific aperture telescope. But the way to get around it is to build bigger and bigger telescopes. But what really limits your resolution is something called seeing. So this is an astronomer's term, and seeing refers to the atmospheric conditions on any given clear night. So if you're at a star party or a public observing session, you will often hear people say, "Oh, the seeing is great." Or if you see stars twinkle a lot in the sky, then people will say, "Oh, the seeing is rotten," because obviously you want the stars to be as sharp and steady as possible, either with your eyes or through a telescope. But you always have some seeing to contend with. The steadiness is always a little rocky. So again, the seeing is said to be poor when the atmosphere is unsteady and produces a blurred image. And it's always a little unsteady. It's never perfect. I mean, there are nights you can get ideal setting, but it won't be as good as it would be in the emptiness of space. But, it's a little hard to look through a telescope in a vacuum. So here's a real world example of this. Here's a nice video of Jupiter recorded through a telescope. And that light from Jupiter, of course, it's all reflected sunlight, but that's not really important. But that light that comes to us from Jupiter is nice and straight and steady and true until it travels through that little bit through Earth's atmosphere. And then the Earth's atmosphere slightly bends and distorts it and gives it this wavy look here. So all in all, though, this is a night of relatively good seeing, because I've done videos like this where it looks like Jupiter, it looks like it's doing hula hoops or the hula or something, because it's just all wavy and shaky and just beyond recognition. So this is actually relatively good here, but this is a night of, a real example of seeing. And of course, what can cause really bad seeing is the jet stream. So the jet stream is created by a convergence of cold air masses descending from the Arctic and rising warm air from the tropics. And boy, do we know the jet stream here in Southwest Michigan, because as you see in the video here, it often passes right over us. So I'm at a latitude of roughly 40 degrees. So our latitude has often been called the roaring 40s because of the way planets and stars look through a telescope, because the jet stream often passes over us, so we kind of have a rotten scene here. But if you want good scene, travel further south. There are further south, like especially down south in Florida, they're very well known for very good scene because they have like 70-degree water, 70-degree air all the time. And so that makes for a very smooth airflow and you get really, really good planet images. But there are those very rare nights, even here in Michigan, where the scene is ideal. I can remember several such nights. Okay, so another important term here is transparency. And this is relevant for your unaided eye or binoculars or a telescope. So obviously transparency refers to the transparency or the clarity of the sky. And so the more transparent the sky, the more stars you can see. And so what can limit transparency, besides obviously clouds, because you can have zero transparency when it's totally overcast, but on a clear night, what limits your transparency, for us, it's humidity, it could be dust, it could be pollution, any of those causes, maybe even very rarely volcanic dust. Or quite often now, every summer, our transparency is limited by smoke from wildfires out west because climate change is real. Sorry, folks, but it's true. So Michigan, again, is not an ideal place for transparency or seeing. So this is not the easiest place to do amateur astronomy, but we tend to get by pretty well. All right, so back to the direct telescope terms. After aperture, the next important term is focal length. And it's exactly what it sounds like. I'll just kind of read it here for you first. It's basically the distance, usually expressed in millimeters, in an optical system from the lens or primary mirror to the point where the telescope is in focus, otherwise known as the focal point. Or in a little more simpler term, it's the distance light travels in a telescope to come to a focus. See, wasn't that easier? So the longer a telescope's focal length, generally the more power or magnification it has. The larger the image, but the smaller the field of view. So there's always a trade-off. So, some telescopes can have a short focal length and they're meant for wide field views. Telescopes with longer focal lengths are more meant for the moon and planets and double stars, areas where you want more magnification. So for example, let's say we have two identical aperture telescopes. Let's just say they're both 8 inches in aperture. They both have 8-inch mirrors, but one 8-inch telescope has a focal length of 2,000 millimeters, and the other has a focal length of 1,000 millimeters. So the 2,000 millimeter telescope has twice the power, but half the field of view of the 1,000 millimeter telescope. So if you had to pick one for planets or the moon or double stars, you want the 2,000 millimeter focal length. But if you want, more wider fields of deep sky regions, you want a 1,000 millimeter focal length telescope. So I already mentioned it. Power is also known as magnification. And this is the ability to make an image bigger, duh. And so to find the magnification of a telescope, you just simply use this equation. And out of all the equations that I will show you today, I think there's at least one more later, but this is the most important one. This is the one you should commit to memory, but thankfully it's very easy. Because if you do share your telescope with other observers, they're going to constantly ask you, what magnification is this? What power is this? How much bigger is the image in the telescope? And you're going to want to be able to calculate that. Usually I try to have like a little table or cheat sheet nearby, because I just never bother to memorize them, because when I'm observing, I don't care. I know which eyepiece gives more power. I don't care what it is. I just know it's good. So to calculate the magnification, you just have the telescope focal length and you divide it by the eyepiece focal length. Because yes, eyepieces, they're just collections of lenses. So they have focal lengths too, which are almost always clearly expressed on eyepieces. So for example, let's say we have that 2500 millimeter focal length telescope. That was the focal length of my first 10-inch telescope, a 10-inch Schmidt-Cassegrain. And let's say we have a 10 millimeter eyepiece. We'll make the math easy. We just cancel a zero there, we cancel a zero there, and we get 250 power. So notice the millimeters cancel. So magnification, as we say in physics, is a dimensionless number. It doesn't have any units, but we always put like a little X there, or sometimes people just type it out. They'll say times. This telescope with this eyepiece magnifies 250 times. And of course, that's the joy of telescopes compared to most binoculars, is that the eyepieces are interchangeable. So you can have a whole range of magnifications. For many years, when I got my first telescope, I basically had one eyepiece and maybe a Barlow lens. We'll talk about those later. But eventually you want to collect at least 3 eyepieces. I'm not even sure how many I have today, but quite a few. So it's good to have at least 3 eyepieces that you can collect over time that give you a range of magnifications. Now, there is a limit to how much magnification you can use before the image becomes too faint and, just too blurry. So the general rule of thumb is 50 power per inch of aperture. So if you do have a 10-inch telescope, 10 times 50, make the math easy, you shouldn't be able to use more than 500 power. So make sure you don't buy an eyepiece that gives you more than that for, this focal length telescope, for example. But again, just multiply 50x by the aperture of the telescope you're looking for, or the one you perhaps already have. Now, again, this is under pretty ideal seeing conditions. For us in Michigan, it's probably about half of this. It's probably about 25 power per inch of aperture, because the seeing is rarely ever ideal here in Michigan. So 250 power, that's about as most as I ever used with my old 10-inch Schmidt-Cassegrain. But again, there are those rare nights, or you travel to somewhere with extraordinary seeing, where you can get a little bit better than this. Because I've been able to get, Mars and Saturn, as big as quarters in the eyepiece. And that was pretty awesome. And there is a limit to how low you can go usually. And that is where you multiply by the F ratio, but we don't really talk about that. But that's more in the notes as well. Oh no, we do get to that. I'm sorry. Okay, so here's a little chestnut I pulled off Craigslist. Maybe once a year or twice a year, I like to go on Craigslist and just see what kind of junky telescopes people are selling. Sometimes you see some pretty nice ones on there, but oftentimes they're junk telescopes that you can clearly tell they've never used because they don't know how to set it up. But it looks like this one here, I can't remember specifically, has always been in the box. But fortunately, you don't see this much anymore. Number one, Tasco is, I think, pretty much long gone now. They don't really make telescopes anymore, if they're even around at all. You could update me if you want to, but frankly, I don't care. But you used to see this a lot with Tasco and Bushnell telescopes that were sold in department stores, where they throw 675 power on the box. And of course, that is complete garbage. There's no way this little junky telescope could ever reach 700 or 675 power and give you a usable image. I mean, technically, yes, it probably does come with the eyepieces and Barlows you need to get to that magnification. But remember, as you magnify stuff, it's going to get fainter. With the inverse square, it's kind of inverse square relationship. So, things get twice as faint or 4 times as faint with twice the magnification. And they get blurrier too, because the more you magnify, the more you bring out the bad scene. So that's why your magnification and aperture are limited by really the given conditions. And so thank goodness this has kind of gone the way of the dinosaur, because these were the bane of amateur astronomers for a long time. There's still plenty of junk telescopes around, but it's not quite as bad as it used to be. Okay, so focal ratio, this is what I thought we weren't going to talk about, but focal ratio, it's really more relevant to the next lecture on astrophotography, but the focal ratio can be a good shorthand to describe the focal length of your telescope as well. So obviously the focal ratio is the ratio of something, and that is the ratio of a telescope's focal length to its aperture. So obviously, to calculate it, you divide the focal length by the aperture. So a telescope with, again, a 2,500 millimeter focal length and an aperture of 10 inches or 250 millimeters, see, isn't the metric system wonderful? 0.25 meters, 25 centimeters, 250 millimeters, has a focal ratio of 10. So 2,500 divided by 250 is 10, and this is specified usually in the telescope manual or on the telescope itself as F10. So if you see an F10 and like an F6.7 10-inch Schmidt-Cassegrain, obviously the F6.7 will be faster photographically or with images. It'll collect light faster than an F10. So F10s are higher contrast for visual use though. So if you wanted to use a 10-inch Schmidt-Cassegrain for planetary use, you want to get an F10 as opposed to a 6.7. But it's the opposite for astrophotography. So that's why this term is more important for really astrophotography than it is for visual use. But for visual use, it's a great shorthand to describe your telescope. So people can say, yeah, I got an 80 millimeter f5. So that would usually be a pretty wide field telescope. All right, so let's get into the telescope types. And for most amateur astronomers, there are really only 3 basic types of telescopes. So it's really simple. The first type is the refracting telescope, also known as the refractor. And usually when people imagine the word telescope in their head, this is the type of telescope they think of. A long, narrow tube with a lens, or in actuality, at least 2 lenses up front. So yes, it does say objective lens, but really it's objective lenses. And we will talk about why we always use at least 2 lenses up front as opposed to 1. So you can see the light comes straight in, but then the objective lens bends or refracts the light. So that's why it's called a refractor, because it bends the light and brings it to a focus. So the refracting telescope was the first type of telescope. We're not exactly 100% sure who invented the telescope, or specifically the refracting telescope, but credit often goes to Hans Lippershey, who in 1608 tried to obtain a patent for it. And in the patent he filed on October 2nd, 1608, he says this was an instrument used for seeing things far away as if they were nearby. You know, a pretty apt description of a telescope. But his patent was rejected because they said it was a pretty common tool already. And kind of so the story goes, people said Hans invented the telescope while working in a spectacle shop, you know, because people were purchasing spectacles even in the early 17th century. Two kids were playing with lenses in his spectacle shop, and they noticed how when they used the right combination of lenses, it made things appear closer. And so again, he tried to get a patent for this, and he wasn't the only person to do so, but no one really ever received a patent for it. And he didn't call it a telescope. I have no idea what Hans Lippershey would have called this device, but the term telescope was coined by Giovanni de Minisani in 1611. And Thomas Harriot has perhaps my more favorite name for it. Thomas Harriot, if you don't know, he's kind of the English Galileo. He observed a lot of the same things, like craters on the moon, moons around Jupiter, the same time Galileo did. Thomas Harriot called the telescope a perspective tube. So I've always loved that term. So perhaps I'll change the lecture to perspective tube tutorial as opposed to telescope tutorial, but then nobody would know what I was talking about. And yeah, so often people think that Galileo invented the telescope. He did not, but he sort of reinvented it and made it a little better for astronomy. So a little background history there. So here are some basic refracting telescopes. And maybe you might be a little disappointed, but I am not going to go into specific brands available today, or at least specific models available today. But, you know, there are many manufacturers of refracting telescopes out there. There's, of course, the usual big three, Meade, Celestron, Orion. Of course, Meade and Orion are the same company now, but there's also Teleview, Astrophysics, Skywatcher, Vixen, and so on. So there are many places that make refracting telescopes today. And so here are several here, like here's a Teleview, here's an Astrophysics, clearly this is a Vixen, this is a Explore Scientific telescope, and you can see they have different apertures. And remember, we always refer to a telescope by its aperture. So this would be a 76 millimeter refractor because the objective lens is 76 millimeters in diameter. This is a 6-inch or like 150 millimeter refractor. So the objective lens here is 6 inches in diameter. Historically, this wasn't always true. Telescopes were often referred to by their focal length as opposed to their aperture, you know, in the 16 or the 17th century, 18th century. I'm not quite sure when the transition came to referring to it to its aperture, but it was definitely in the late 19th or early 20th century, because you can still see it pretty late in the historical record. So they have different apertures, and they obviously have different focal lengths. Obviously, the big one here, or even this one, they're a bit longer focal length, so they're really good for the planets. This one would be more suitable for wide field views of the night sky, you know, taking in wide swaths of star clusters and stuff like that. But even little boogers like this can be, you know, pretty decent for the planets. But obviously, if you're more attuned to just observing the moon and planets, you want to get a longer focal length refractor. So let's check out the pros and cons of each type. So for the refractor, the pros are it is the easiest to use and the most reliable due to the simplicity of the design. I mean, they require very little, if no maintenance. Very rarely will you have to clean the objective lens. But if it came to you properly from the manufacturer and you don't drop it, the objective lens is permanently mounted and aligned. So they don't require frequent alignment, or as we say, collimation. So the sealed optical tube reduces image degrading air currents and protects the optics, at least on the inside. So you never have to worry about dust and humidity getting on the inside of the telescope. So you have to like take it apart or something. And refractors are known for their high contrast images because they have no central obstruction. We'll see that later with reflectors and catadioptric telescopes. They all have a central obstruction because of their basic design. And so, because refractors are known for their high contrast images, these are the telescopes of choice for lunar, planetary, and binary star observing, especially in the larger apertures and longer focal lengths. And so there are two general type of refractors. There's achromatic refractors and there's apochromatic refractors. Achromatic use glass like flint and crown glass. So they use two different types of glass together. While apochromatic refractors can use several varieties. I won't name all of them, but apos can use ED glass or extra low dispersion glass or fluorite, and there are many other exotic designs. And you'll see why we have different glass types and refractors today. So the color correction, and this will become more clear again shortly, is pretty good in most achromatic refractors today, but you will see some color issues around bright objects like planets and stars. But it's excellent in high-end, but really expensive apochromatic refractors. And pretty much binoculars, for example, and most spotting scopes are refracting telescopes. So if you have a small refractor, it can be used for a daytime telescope as well to look at birds and other types of wildlife. So refractors can be multi-purpose telescopes. Of course, you can use like a 6-inch refractor to look at birds, but it's not exactly a quick portable way to take it out to the field to look at birds. Okay, so here are the cons of a refracting telescope. The first one is your pocketbook. They are the most expensive per inch of aperture, especially in the apochromatic design, because boy, do they get expensive as they get bigger. So the cost and bulk factors, because as they get larger in aperture, they get very long, limit the practical, useful, maximum size objective to small apertures. So you can buy refractors for visual use, at least, roughly from 50 millimeters, about 2 inches, up to about 6 inches. You don't see too many refractors available on the commercial market today that are larger than 6 inches in aperture. Maybe there are some examples I'm not remembering out there, but that's generally true. You know, here in Michigan, on the campus of Eastern Michigan University, they have a 10-inch refractor, and that thing's like, 2 subcompact cars long. It's like maybe over a minivan in length. So as they get larger in aperture, again, they get very, very long or very large. So they're just not practical to take anywhere. So because refractors are limited in aperture, they are less suited for viewing small, faint, deep sky objects because with faint, fuzzy galaxies, you want as much aperture as you can. So refractors aren't the ideal thing for that. So if you do want to observe, deep sky objects, you want to probably be steered more to one of the other designs. They are good for deep sky objects, for wide field views, but if you want to see really faint stuff, they're not the best to get. And again, they're heavier, longer, and bulkier than equivalent aperture reflecting telescopes. A 6-inch reflector is a lot more portable than a 6-inch refractor. And definitely a 10-inch reflector is a lot more portable than a 10-inch refractor, as I mentioned here. And if you do drop them, or you somehow get them from the manufacturer and they're out of collimation and you miss the warranty, they are difficult to collimate on your own. Some refractors I've seen do have the ability to be collimated easily by people, but most don't. You usually have to take it apart, take the mirror cell apart, and collimate it yourself. And for a lot of people, that's too much. So if you do drop your refractor, you'll probably have to send it back to the manufacturer or maybe a dealer to get it collimated. And of course, some have color aberrations, especially the achromatic designs. So this gets us in to the color issues that I alluded to earlier. So achromatic refractors, they suffer from what's called chromatic aberration. It's been greatly reduced, and there are ways to subdue it a bit, but still, it's not the telescope performing at its absolute best. So here's a single lens. And lenses don't want to, but they can act like prisms. You know, prisms on purpose break up white light into its constituent colors, you know, red, orange, yellow, green, blue, violet. There is no indigo, by the way. So here we have white light come in, and when it's bent and refracted by the telescope, the various colors of the white light, which have different wavelengths, don't come to the same focus. Now, with achromatic refractors, they tend to focus the red and blue light pretty well. It's not as bad as I show here, but obviously this is a single lens. So that's one reason achromatics use flint and crown glass together, because they both have properties that help bring the red and blue light together. But the more modern apochromatic refractors, they use, again, more expensive glass, more modern glass that of different types that bring all the colors to the same focus, you know, to the same focal point. So what does this look like through a telescope? Of course, it won't be this severe here because there's only one lens here, but here's a view, you know, what otherwise looks like a nice image of the Andromeda galaxy. And around a lot of the bright stars in this image, you see little purple halos. And that purple halo is called a secondary spectrum. And that is a sign of chromatic aberration. Now, there are filters you can put on your eyepiece to obscure this. They're called minus violet filters, but still all the colors are not coming to the same focus. So when you compare a 6-inch achromat to a 6-inch apochromat, you can clearly see the difference. Even newbies can tell the image is far superior in a 6-inch apo as opposed to a 6-inch acro. But the person with the 6-inch apo paid a lot more than that 6-inch acro. So there are definite drawbacks to quality. You usually got to pay for it. All right, here's the next type, the reflecting telescope. And there are many different types of reflecting telescopes. The specific one shown here is a Newtonian reflector, invented by none other than Isaac Newton himself in 1668. And so it looks a lot different in design. So the light comes in, and guess what? At first, nothing happens. There's no lenses up front. But when the light strikes the primary mirror, which has a concave parabolic curve to it, the light is reflected up in kind of a cone here. And then it reflects off the flat secondary mirror at a 45-degree angle, and then it comes up to a focal point and magnified by the eyepiece up here. So it's a little more complicated than a refractor, but not really so much more. And ironically enough, these are easier to make than refracting telescopes, even though they look a little more complicated. So here are some basic Newtonian reflectors. Here's the famous Edmund Astroscan. I heard recently they haven't made these in a while because they literally broke the mold. They broke the mold by apparently accident, and they didn't bother to make any more. So they can't apparently make these anymore because they broke the mold. And this is a nice tabletop telescope that Celestron makes. They still make them, and I bought one of these, but just for a tabletop display. So again, as you can see, they come in a variety of apertures. This is like 76 millimeters, if memory serves, and they can come up to much, much larger sizes. And you can see some are a bit longer, Here's an old Parks Optical. I believe they have since gone out of business. So I show this kind of for historical perspective here. Some are longer and some are shorter in focal length. So obviously the ones that are a bit longer are probably better for the moon and planets. Those that are shorter are meant for more wide field sweeping views of the sky. So here are the pros of a reflector. The most important one is, again, your pocketbook. They are the lowest cost per inch of aperture because they are so easy to make. They are so easy to make that many people still choose to grind their own mirrors and build their own telescopes from scratch. So because they are so easy and cheap to make, they are available in the widest range of apertures. Again, I believe the smallest you can get is about 76 millimeters. The largest you can get currently, I think, is around 32 inches. Big, big telescopes. So because you can buy a big one for a relatively low price, these are the telescopes of choice for deep sky objects. So if your obsession is going to become observing faint nebulae, star clusters, and especially galaxies, you want to get yourself a big Newtonian reflector. Now, reflectors have no lenses except for the eyepieces. So they have no chromatic aberration. And the optical aberrations they might have, especially in the faster designs like a 8-inch f4, for example, will have coma, where stars look like little comets on the edge of the field. But for a relatively low price, you can buy what's called a coma corrector and basically correct for that. So again, the optical aberrations are very low and they deliver very bright images, especially in the larger apertures. And those optical aberrations they do have, for the most part, they are easy to correct. Now, the larger types that are a bit longer in focal length, like say an f6 or an f7, they are still pretty good for the moon and planets. When you compare them with a similar sized refractor, I mean, the refractor is going to kick its butt, but still, they deliver very good, respectable views. There really isn't anything to be ashamed of there. They'll do you well. And they are still reasonably compact and portable up to focal lengths of about 1,000 millimeters. But even really large versions can be a lot more portable than you might imagine. And the higher end models are just excellent for deep sky astrophotography. There's like ASA astrographs. They're very nice Newtonian reflectors that are just excellent astrophotography telescopes. If you happen to have one lying around you're not using, feel free to send it to me for free. Okay, so here are the cons. They are not suited for terrestrial use, especially Newtonian reflectors, because I didn't mention the pros and cons I'm talking about are specifically for a Newtonian reflector, because there are some reflectors that you can use for daytime use. But Newtonian reflectors show everything upside down and inverted. So who wants to look at a bird, in a tree that's upside down? Not me. So you don't want to use a Newtonian reflector for use during the day. There are ways to correct for that, but it degrades the image. So why bother? Now, as I mentioned, they do have an open air design. The light just goes straight in. So if you use it outside a lot, especially in Michigan where it's humid, your primary mirror is going to get dewed up a lot, and you might have to take out the primary mirror every so often to clean it. But the first rule with cleaning your optics is don't. If you think you need to do it, you probably don't need to do it. But eventually it's going to get to the point to where you probably do need to do it. But I'm not going to get into cleaning optics today. That's a little beyond the scope of the series here. And maybe, with prolonged use, you might even have to get the mirror re-illuminized too, or re-silvered if you have a rare one that's silvered instead of with a coating of aluminum on it. And they do have that secondary mirror. So that secondary mirror does block some of the light. So there is a bit of a light loss. And they do have two different mirrors, the primary and the secondary, and they require frequent collimation, especially in larger apertures. Basically, if it's 6 inches or larger, you probably have to collimate it every time you take it out. And for the beginner, that's scary. They just don't like to tweak the optics. But with enough practice and with the right tools, with like a Cheshire eyepiece and a laser collimator, it gets really easy to collimate your reflector. And of course, there are plenty of people in astronomy clubs, if you have one nearby, that can help you with that. And I mentioned they do suffer from off-axis coma, where the stars look like little kind of comets toward the edge of the field of view, but just throw on a coma corrector and you'll be fine. And the larger apertures over 8 inches can still get pretty bulky and heavy, and do tend to be more expensive, but nowhere near as bulky and as expensive as a similar sized refractor, because get up to 8-inch refractor and you really got to put it in a observatory. It just gets too big. All right, our third type, we kind of get 2 for the price of 1 here, is the catadioptric telescope. The one specifically shown in the graphic here is a Schmidt-Cassegrain, by far the most common type. Another one that's also fairly common is the Maksutov-Cassegrain, but it's almost exactly the same. So these are hybrid telescopes. They have properties of refractors and reflectors, but by and large, they're mostly reflecting telescopes. So what gives them a property of a refractor is they do have a lens up front that does help correct the image a bit, because the tubes are so short and stubby, because they're made to be very portable. So in the case of the Schmidt-Cassegrain, the lens up front is so thin, it's called a corrector plate. In the case of a Maksutov-Cassegrain, it's called a correcting lens, because it's a little thicker and curved, but they're almost exactly the same. So when the light does come in, it doesn't show in the graphic here, but it's ever so slightly bent, like a refractor, but not nearly as extreme as a refracting telescope does it. And then when it's corrected by the correcting plate, it reflects off a kind of aspheric lens here, or mirror, not lens. And then it comes up to the secondary mirror, and then through the hole in the primary. And yeah, there is a hole in the center of a primary, but it's in the shadow of the secondary mirror anyway. So, why not put a hole there? No light would fall there anyway. And then it comes to a focus down here. So Schmidt-Cassegrains, I can't really say who invented them, but it was Tom Johnson at Celestron that marketed the first Schmidt-Cassegrains in the early 1960s. And so they became very popular because, as you can see in the image here, Schmidt-Cassegrains are very short, stubby-looking telescopes. They really are light buckets. That term applies really for all telescopes, but more so for Schmidt-Cassegrains, because it does look like they're maybe made out of a aluminum trash can almost. But of course they're not really. In this case here, all Schmidt-Cassegrains pretty much look the same in terms of focal length, but of course they come in a variety of apertures. I think you can get Schmidt-Cassegrains from 4 inches, maybe 5, up to 16 inches. Celestron used to make a 20-inch, like back in the 60s and 70s, but they haven't done that in many, many years. I've never even seen one, not even a used one for sale, but they're out there. So most Schmidt-Cassegrains, the most common type is an 8-inch. They're very, very common. In fact, the C8 has again been around since the 1960s. So Celestron and Meade, they have basically perfected the design. Most Schmidt-Cassegrains today even have coma correctors in the back of the optics here that give even better images than they did in the 60s, 70s, and 80s. So here are some examples of Maksutov-Cassegrains. And you can see they always have this little silver point. I don't believe that has any special function. It's just something that a lot of Maksutov-Cassegrains have. Not all of them do, but you can't really tell from the image. You can maybe tell a little bit here, but you can see the correcting plate is actually curved, and it is thicker, so that's why it's known as a correcting lens. So Maksutov-Cassegrains, they're always longer focal length and higher in F ratio than a similar sized Schmidt-Cassegrain. So I've looked through like a 7-inch Maksutov-Cassegrain, and man, they give excellent high contrast images of the moon and planets and really good color correction. They really give apochromatic refractors a run for their money. And these were invented by Dmitry Maksutov in 1944. And again, they used this deeply curved full diameter negative meniscus lens. They're probably most famous from the Questar telescopes, which are very high quality. So again, if you just happen to have one of these around collecting dust and don't want it, please send it to me for free. They have a titanium design, and man, they are just beautiful. Even in the 1970s, these things sold for a couple of $1,000s. So they are excellent quality telescopes. You're very lucky if you have one. And if you don't want it, again, send it to me. Okay, so here are the pros and cons. And again, this is specifically for a Schmidt-Cassegrain, but it's almost the same for a Maksutov-Cassegrain. So many consider the Schmidt-Cassegrain to be the best all-around, all-purpose design. They're not as good as refractors in terms of their razor-sharp images, but they do it pretty well. So they do have excellent optics with razor-sharp images over a wide field of view. So they are good for lunar, planetary, and binary star observing. As well as a good large apochromatic refractor? No, but they are a fraction of the cost. And most have decent apertures, so they are good for deep sky observing or astrophotography. As good as a Newtonian reflector? Not necessarily, but they're a lot more portable. They might not be cheaper, but they can be more portable, especially in 8 inches and 10-inch designs. And just like refractors, they have a closed tube design, which reduces image degrading air currents on the inside, so you never have to clean the primary mirror or the secondary mirror of a Schmidt-Cassegrain or a Maksutov-Cassegrain, but you might have to clean the front of the corrector plate or the correcting lens every so often. And of course, the main advantage, the reason they were invented in the first place and marketed so much, starting in the 60s and 70s, is they are extremely compact and portable, because light pollution really rose in the 1950s, so people were looking for more portable telescopes to take out to the country, and Schmidt-Cassegrains really filled that role. But today, there's lots of portable refractors as well, and they are pretty durable and virtually maintenance-free. They still need to be collimated from time to time, but not quite as often as a Newtonian. But still, from time to time, you'll have to collimate them. So here are the cons. They are more expensive than Newtonian reflectors of equal aperture. You will definitely pay more for an 8-inch Schmidt-Cassegrain than you would an 8-inch Newtonian. And their secondary mirrors are larger than Newtonians, at least most of them. So again, you have a slight light loss due to a secondary mirror. So that's what limits their resolving power, their resolution. And they are compact and kind of thick for their size, so they do take longer to reach thermal equilibrium. So if it's like 30 degrees outside and you bring your telescope outside where it was 70 degrees, and you try to look through it right away, images will look very blurry and the scene will look terrible because the telescope itself is still giving off heat to space. So you have to give Schmidt-Cassegrains a little time to cool down, at least more so than refractors and Newtonians. Maksutovs are even worse because their optics are even thicker, especially that correcting lens. Now, here's the biggest problem with Schmidt-Cassegrains is they focus with a knob in the back and they move the primary mirror, the entire primary mirror. On smaller apertures, it's not as severe, but in larger apertures, when you adjust the focus, you can see the image shift. And my club, the Kalamazoo Astronomical Society, used to have a 12-inch in our observatory, and that was the worst example of a Schmidt-Cassegrain I ever seen. It was great when it was new, but over time it got worse. When you focus that thing, the image would shift, and when you got the focus in place, the primary mirror would slip and you would lose focus. So you'd have to like lock it down. So that's just one problem you can deal with. You can install a regular like focuser on the back, but not every Schmidt-Cassegrain works well with that. And again, they do have a narrow field of view compared to faster Newtonians. Most Schmidt-Cassegrains are f10, while most Newtonians are f4 to f8. So they have a narrower field of view. And again, as they get larger in aperture, especially 10 inches and up, especially the variety that come with fork mounts, they get really, really heavy. So once you get a telescope, hopefully it either comes with or you'll have to get yourself a good telescope mount. So let's learn about the basic types of telescope mounts. The most common type of telescope mount is a German equatorial mount, which I assume was invented in Germany, but I really don't know the history of a German equatorial mount. So here's your basic German equatorial mount with a, I believe, 9 1/4 Schmidt-Cassegrain on top of it. So you do have a telescope on one end, and which means you have to have a counterweight or counterweights to balance it on the other side. And imagine you have the horizon here running parallel to, say, the bottom of the slide. And so notice the mount itself is at an angle. And of course, that specific angle here depends on your latitude. So you can see it's roughly set at a mid-latitude of about 40 degrees. And you have to set up your German equatorial mount a very specific way. So this end here has to point toward the North Celestial Pole. So there's usually a little polar scope here, not always, but you can look through the polar scope and basically put Polaris in the proper spot of where it says to in the polar alignment scope, and you should be reasonably polar aligned. And so I don't have this animated, but the telescope kind of spins around on the declination axis and swings back and forth on the right ascension axis here. So that is your basic German equatorial mount. And now that we learned a little bit about the basics of a German mount, you can just see how messed up this old advertisement is. I just loved showing this. I got this from Terence Dickinson when he gave a presentation for the Kalamazoo Astronomical Society back in 2011, I believe. And I just can't believe how wrong this is. You can obviously tell the people that put this ad together had no idea how telescopes worked. So here we have a Newtonian reflector on a German equatorial mount that, yes, is set for the equator. I mean, yeah, maybe they are on the equator, but these types of mounts, they really don't work well on the equator, but most people don't live on the equator, and most people that do live on the equator don't have telescopes. So you never see a German equatorial mount set up like this. It's just completely wrong. And so the telescope is pointed at the ground. So of course, this is where the light comes in off the primary mirror, and they're looking backwards through the finder scope. The finder scope is mounted backwards, ladies and gentlemen. It's supposed to be pointed the other way to allow you to find stuff with the telescope when it's pointed in the night sky. So it just shows you how little your average everyday person knows about telescopes. I've even been to secondhand stores where people may drop off a telescope and they have them set up in the store and it's set up wrong. So I'll fix it for them. I can't help myself. Okay, back to some serious stuff here. Okay, so this is new to the lecture. These mounts have become much more prevalent in the past several years, so I decided to throw them in here. And these are known as harmonic drive mounts. They're also known as strain wave gear mounts, but when I say strain wave, it makes me feel like I'm talking about some kind of virus or something. So I tend to prefer the term harmonic drive. It just sounds more, harmonious. So I believe these really came about in the mid 2000s. I can remember a line of harmonic drives coming out in the mid 2000s, and they were very large and very expensive. And I don't know anyone that ever bought one. I've never seen one. So they really didn't catch on until they started making smaller, more portable ones. I could be wrong, but I'm guessing Rainbow Astro. These are Rainbow Astros here. They came out with the first smaller, more portable harmonic drives, and they've only increased in popularity. And just a short time ago, just a couple years ago, really, ZWO came out with the AM5. And then even more recently, they came out with the AM3. So again, these are both harmonic drive mounts. And then more recently, Ioptron has a whole series of them. There's just a few of the models here. Many of them, like the EC models, have what's called absolute encoders that make the mount very precise in terms of its tracking. So there are a whole variety out there, and the main advantage of harmonic drives, as you can kind of tell maybe from the image here, is look, no counterweight. I mean, they do have the ability to attach a counterweight to them if you have a really heavy payload, but that kind of defeats the purpose of a harmonic drive mount. They're relatively small for their size, and they have a large load capacity. So in terms of portability, especially if you have to fly somewhere, like for the eclipse, for example, these are excellent mounts to have if you have to travel by air to, a star party or to some eclipse site. So, for example, the RST 135E shown here, this has a weight capacity of 30 pounds or 13.5 kilograms without counterweights. It gives you a load capacity with counterweights, but I didn't make note of that. So I wish I put something in here for scale, but believe me, these are relatively small mounts. And the RST 300 here, this has a capacity of 66 pounds. I mean, which is that's a lot. Most German equatorial mounts you can get for a reasonable price don't have weight capacities of 66 pounds, but this mount here is $8,500. So that is kind of one of the disadvantage of harmonic drives is they do cost a bit more. So they are out there. They are excellent, but they are expensive. So the next type of mount, and many of the harmonic drives I mentioned can be used in this style, but here we have the classic cheesy all-azimuth mount. But don't let that cheesy comment fool you. There are lots of really good all-azimuth mounts out there. So all-azimuth is the abbreviated term. The full name is altitude azimuth mount, but of course we abbreviate it. You can even call them all-az mounts to be even briefer. And as the name suggests, they move in azimuth and altitude. So you can point the telescope in azimuth, in different directions in the sky, and you can move the telescope up and down in altitude as well. So these are the mounts to get if you want to do both day and nighttime viewing, not necessarily looking at the sun during the day, but wildlife. So all azimuth mounts are, great for bird watching and astronomy at night. And that one is pretty cheesy, yes, but here are some much nicer all azimuth mounts. Some are not motorized, like this one, and many have go-to capability now. Here's one from Skywatcher that's very portable, not very expensive, but does have go-to capability. And here's one from Ioptron that has go-to capability. Some like this one or the one from Los Mandy, if you do like well-machined stuff with a higher capacity than these versions, there's this one by Los Mandy, the AZ8. This has dual mount capacity. You could put like a Schmidt-Cassegrain on one side and your refractor on the other. Or, you know, for solar, a white light scope on one side, a H alpha scope on the other. We'll talk more about those here shortly. And this is one of those harmonic drive all azimuth mounts that I mentioned. I think Ioptron makes this one, but don't exactly quote me on that. So there are certainly plenty of mounts out there today in both the equatorial and all azimuth variety, but probably by far the most popular type of mount that is an all azimuth mount is the Dobsonian telescope mount. Many people think Dobsonians are a different type of telescope, but Dobsonians are Newtonian reflectors on this kind of rocker box design that makes it a Dobsonian mount. And this type of mount was invented by John Dobson, who passed away in 2014. He probably could have became a millionaire. He could have started a telescope company that exclusively sold these telescopes, you know, but no, he gave away the design freely. Companies just took it and ran with it because he wanted to make larger aperture telescopes much more portable. And that's what Dobsonians do. Previously, with maybe a 10-inch or 12-inch or 16-inch or even a 30-inch Newtonian reflector had to be on a massive equatorial mount that just made it impossible to transport anywhere, and you had to put it in an observatory. But Dobsonian mounts make large aperture Newtonians just a whole lot more portable. Some are still pretty bulky, but relatively speaking, they are extremely portable. So here's one example of that in the extreme. These gentlemen look very pleased with themselves here. We have two 25-inch Dobsonians. So they each have a 25-inch mirror, primary mirror that is, and this is a 20-inch. Now, I've looked through plenty of big Dobsonians, mainly at star parties around the country, like the Winter Star Party and the Texas Star Party. And when you do look through one of these, you do get a affliction called aperture fever. It is very contagious. You look through one of these and you say to yourself, I've got to get me one of those. But I have the ultimate cure for aperture fever, and it is known as poverty. So I would love to get one of these big hulking telescopes, but I can't. I'm poor. So here's an example, just this one story of mine is I was at the 2005 Winter Star Party, and one of our members had a 20-inch Obsession set up. Very nice telescope. Obsessions are Dobsonians made in Wisconsin. And he pointed it at the best globular cluster in the sky, shown here, Omega Centauri. And the eyepiece he had, you know, we'll get to eyepieces, is a 31 millimeter Nagler Type 5. And I believe he used a 2x power mate as well. And so this approximates that field of view. And so when I walked up and looked through the eyepiece, I screamed very loudly just because I was so astonished. Holy expletive, you know, I'll censor myself there. And people just came running. They were like, what's wrong? What's wrong? And the guy with the telescope said, oh no, Richard just saw Omega Centauri through my 20-inch telescope. And they were like, oh yeah, that's totally understandable. And so of course, suddenly we had a big long line of people come to look through the telescope. And I can remember very nice views of the trapezium region of the Orion Nebula with the same telescope. So yeah, a 20-inch Obsession can give a view very much like this. And I don't believe a Obsession makes one this big anymore, but here's a 30-inch Obsession, at least the business end of it, at the 2010 Okie-Tex Star Party, the only time I went to the Okie-Tex Star Party. And this telescope is kind of famous. This is the 36-inch yard scope. that I'm not sure if he still owns it, but this was owned by Crazy Bob Summerfield. He was a mainstay at many star parties over the years, but I'm not sure whatever happened to him. I heard his health may have deteriorated a bit, but again, don't quote me on that. And I did get to look through this telescope at the 2001 Texas Star Party at the Whirlpool Galaxy, and it looked like one of the sketches from Lord Rosse in Ireland did through his 72-inch telescope. And then I also got to look through this telescope at the Winter Star Party, shown here, because obviously this isn't West Texas, at the Horsehead Nebula. And it was so easy to see the Horsehead Nebula through a scope this big. Now, I believe the world's largest amateur telescope is this one here. Here is Mike Clements, and this is a 70-inch, 1.8 meter Dobsonian. Now, it may not be the record holder anymore, but I don't know, 70 inches is pretty hard to beat. So he clearly had to grind his own mirror, which is 70 inches across, by the way, and that must have taken many, many years. I've only heard about this telescope. I've never seen it. And thank goodness he only has this out on clear nights, because if a storm came in, this thing would get struck by lightning. And there's one fun advantage of a large aperture Dobsonian, especially at a star party, is you can use them for shade. I took this one at the 2010 Okie-Tex Star Party, and I was like, hey, that's a unsung benefit of large aperture Dobsonian telescopes. But just remember, the whole point of telescopes is to, hopefully get as large as aperture as you can afford and find portable, so you actually want to take it out. And the larger the aperture, the brighter and sharper things become. And that's very clear in this graphic from Obsession telescopes. So yeah, an 8-inch telescope will kind of give a view of a globular cluster like M13 like this, but the larger the aperture, the brighter and sharper things become. But, there's pocketbook and just practical portability requirements. So here is some purchasing advice. Number one, as I've been stressing throughout the entire series, educate yourself. Once the introduction to amateur astronomy lecture series is over, you can review the notes that I have given you. You can buy the books I've recommended. You can check out some websites and maybe talk to people in your community, but it's going to be up to you to basically teach yourself this stuff. So that's why the most important bit of advice that I can also give you is, if you have one, join your local astronomy club and attend their star parties. Let me back that up and do it again. Join your local astronomy club and attend their observing sessions. I mean, you can look at a telescope on a showroom floor if you're lucky enough to have a telescope dealer in your town, but nothing will tell you as much as looking through the telescope, seeing what it's actually like in person, and talking to the owner. Because if they've owned the telescope for at least a year or more, they're going to know all the ins and outs and all the pluses or minuses of specific designs. So attend a local observing session or go to a national star party. Especially at a national star party, you will see every type of telescope design imaginable. And even before you buy a telescope, see if the astronomy club that you may have in your town has a telescope loan program. I can tell you the Kalamazoo Astronomical Society does. We have an 80mm refractor. We have an 8-inch Schmidt-Cassegrain, and pretty soon, once we get past the craziness of the eclipse, we'll have a 5-inch go-to reflector available. And as I mentioned, attend those star parties as well. And when you get down to a specific telescope model, just read the reviews, either on the dealer's website or definitely get on the forums like Cloudy Nights and stuff like that. And if you forget everything else, if you forget all the other advice, the one thing you shouldn't forget is never, ever buy a telescope at a department store. They are all, without exception, just in plain simple language, Garbage. Do not buy them. They are all junk. I've never seen a good one. So if you see a good meal, a good meal, a good deal at Walmart, it's not a good deal. You're getting ripped off. Don't buy it. Get yourself a good pair of binoculars instead. And of course, purchase a telescope from a reputable dealer. And if you do have a telescope shop, a knowledgeable salesperson. Uh, if you can deal with a salesperson in person, ask them what telescope they own. If they don't have one, they haven't a freaking clue what they're talking about. You got to really use them to know them. All right, so I probably won't be able to talk about every type of telescope accessory here today, but I'm going to mention all the really popular ones. Of course, by far, the most popular one are eyepieces. And just FYI, this is my 9¼ here, as I was observing an occultation of a star with a waxing gibbous moon up here. And this is my Celestron C gem that I did sell, and I bought an Astrophysics Mach 1, which is far superior. So here are just some various eyepieces. And again, there are lots of eyepiece manufacturers out there, but I have a special place in my heart for Teleview Optics because I love Uncle Al. He's a great guy. Al Nagler, the founder of Teleview Optics. So if I can afford it, I try to get Teleview eyepieces. They are expensive, they can be heavy, but Teleview makes excellent quality eyepieces. But many other places make really good eyepieces as well. You really can't go wrong with most mainstream eyepiece folks today. So there are three basic barrel designs. The department store telescopes and pretty much all junk telescopes come with 0.965-inch diameter barrels, you know, the part that slips into the focuser. So again, you want to avoid these. If the barrel is about the same size as a quarter, you don't want to get 0.965 eyepieces. They're all pretty obsolete designs anyway. The standard size is 1.25 inches. That's been the standard size for decades, a very long time. But now, especially starting in the 1980s, thanks to Teleview, 2-inch eyepieces have become very prevalent. And many 2-inch eyepieces just have very wide, expansive, apparent fields of view. They are heavy, they can be expensive, but man, when you look through them, it's like looking through the porthole of a spaceship. So be sure you get either 1.25 inches, or if you can afford it, 2 inches, because those are the way to go. So there are lots of eyepieces. I'm going to zip through this kind of quick here. Huygens was invented by Christian Huygens in the late 1660s, and they were the first compound or multi-lens eyepiece, but, you know, 1660s, folks, it's an obsolete design. You still see them. Maybe with used telescopes like old Tascos and Bushnells you might find on, you know, Craigslist or in yard sales. But obviously, I don't believe you can purchase these commercially anymore. You just find them on the used market. They can be great for solar projection because, you know, you don't need any serious optical quality to do projection. But really, they're not good for anything. And Ramsden's, you can see I'll just kind of flip back and forth here a couple times. It's just they flip the lens over. So they're also two lens elements. They have very narrow fields of view like the Huygens eyepieces. And again, frankly, it's just an obsolete design. So if you do see these out there, you'll see they'll have like SR4 or, you know, SR, whatever the focal length is. This is a 4mm, which is like next to worthless. You know, a 4mm eyepiece just ain't worth much unless you have a really good refractor or something. So if you do see any Huygens with an H on it or Ramsden with the SR, just don't even look at them. Now, back when I started in amateur astronomy, like 40 years ago, Kellners were the minimum. Kellners can be pretty decent quality. You know, they're a big step up from Huygens. And these were developed by Carl Kellner in 1849. And so these are the first modern achromatic eyepieces. But again, 1849. They're pretty old. There are lots of better designs out there, but you can probably still find some Kellners out there on the used market that are just dirt cheap. I if there are some sold brand new out there, I don't know where. But again, they're not really worth anything, and there are better ones out there that are also very affordable. Now, orthoscopic eyepieces, now we're getting into ones that if you do see them maybe used out there, yeah, sure. If they're cheap, why not buy them? Or orthoscopics are decent quality. You know, they have 4 lenses, a modest field of view, and they're known for really excellent contrast, you know, for planetary views, but they do have internal reflections. So today, the minimum standard are the Plossls. You know, in the early 1980s, when Teleview came out with the first line of Plossls, they were new and exciting, but today there are so many out there. This is the industry standard today. So lots of telescopes still come with like a, say, 25 millimeter and 10 millimeter Plossl. And you can find Plossls for, you know, that are brand new for probably $20-$30. So that's why all the previous versions, the Huygens, the Ramsdens, they're just obsolete because Plossls are so plentiful, used or new, and they give really good quality. Now the Erfel eyepiece, these were invented by Heinrich Erfel in 1921, and these are the first wide field eyepieces that give large apparent fields of view, you know, 60, 70 degrees. They do have some astigmatism on the edge, so that's why Erfels aren't as popular as they used to be, because they've been replaced by more modern wide field designs, specifically the Nagler eyepiece. So here's the venerable 31 millimeter Type 5 Nagler I mentioned earlier. This is the only eyepiece that I know of that has nicknames. It's known as the Holy Hand Grenade or the Terminagler. And so these do have lots of lens elements, 6 to 8 lens elements, depending on the specific eyepiece. And all Nagler eyepieces have 82-degree apparent fields of view. They have very few edge aberrations, but they are kind of heavy. They might throw your Dobsonian off balance, and they do tend to have a high cost. You know, the 31 Nagler brand new is around $700, but they've been out for many years. I got mine on Astromart for about $400, which is still expensive, but still, it's worth it. It is an excellent eyepiece. Even newer from Teleview and now often replicated from other manufacturers are their Ethos design, most of which have a 100-degree field of view, but some of the shorter focal length ones have a 110-degree apparent field of view. And again, they have very few aberrations, but like the Naglers, they are heavy and the cost is even higher. The Ethos here, the 21 millimeter, that approaches $800 or so. I mean, you know, yeah, an eyepiece costs more than lots of telescopes out there, you know, good sized telescopes. It's crazy. But boy, there are lots of excellent eyepieces out there today. So if you don't want to spring for the Televiews, I think you'll be happy with pretty much all the others from Meade, Celestron, Skywatcher, and so on. Okay, so I mentioned all these eyepieces have an apparent field of view. Now, you can calculate their true field of view with my last equation here today. So to calculate the actual field of view with your eyepiece and telescope, you take the eyepiece's apparent field of view, and you use the magnification equation earlier to calculate the magnification, and you plop that in here. So, for example, what is the actual field of view of a 31 millimeter Nagler used with a 2,350 millimeter focal length telescope? FYI, this is the focal length of my Celestron 9 1/4. So what is the magnification, or what is the true field of view with my 31 Nagler and my 9 1/4 inch Schmidt-Cassegrain? So again, all Naglers have an 82-degree apparent field of view. 2350 divided by 31 is 76, and that gives me 1.1 degrees. So I can fit 2 full moons. Thank goodness we don't have 2 of them. One's enough. But I could theoretically fit 2 full moons in the field of view of that eyepiece. So it gives you a very nice wide field of view. All right, so if you buy a refractor or a Schmidt-Cassegrain, it's probably going to come with a diagonal. Quite often, they might just come with an 1.25 inch diagonal, but you might want to upgrade to a 2-inch, because if you want to use 2-inch eyepieces, you got to have a 2-inch diagonal. So there are 2 basic types out there. You can see there are mirror diagonals. Some of them mention they have a mirror. At least I think some of them do. Here's one. And some mention they have a prism. So mirror diagonals cost less to produce high quality views compared to prism diagonals. Mirror diagonals do not introduce any color errors to the image, and they do have a dielectric coating that does not deteriorate. So most mirror diagonals do have the high coatings that reflect like 98% of the light today. Prism diagonals do use either a pentaprism or an Amici prism, and they may introduce chromatic aberration, especially with short focal length telescopes. So if you do want to get a prism diagonal, like say this one, make sure you have a longer focal length telescope, because then you'll be fine. And if you do want to use your telescope like your refractor or even your small Schmidt-Cassegrain or Maksutov-Cassegrain during the day, then you want to get yourself a 45-degree diagonal. So if you do use a 45-degree diagonal, it gives you a corrected image. It even says correct image diagonal on here. You can convert any refractor or Schmidt or Maksutov-Cassegrain into a daytime telescope with the use of one of these diagonals. I don't know of one that comes in a 2-inch design. I just don't know of one. If they have one, I don't know about it. Now, I will mention, if you want to get a 2-inch diagonal for your Schmidt-Cassegrain, they do have diagonals specifically meant to thread onto Schmidt-Cassegrains, but I don't like them because it's more difficult to rotate the eyepiece for like the public or even yourself. So it's better to use a diagonal meant for a refractor on a Schmidt-Cassegrain. They do have adapters to do that, and you just loosen the set screw and it turns a lot easier. So I would not get the dedicated Schmidt-Cassegrain diagonals. And if you do have a refractor or a Newtonian with kind of a junky focuser, there are plenty of upgrades out there. Now, I do know that Moonlight Focuser, who makes this nice Crayford focuser, does not produce these anymore. They only have motorized focusers now. They no longer have a manual one like this one. So I'm glad I bought mine when I did for my 8-inch f4 Newtonian. So Crayford focusers are gearless. They basically work by friction. And the heavier ones from like Moonlight, if you can find them used, they are pretty good. But the ones that, like I have an Astrotech 8-inch f4, the Crayford focuser on that was garbage for astrophotography because it would slip all the time. For visual use, it's not that big a deal. You just tweak the focus real quick. But for astrophotography, you'll definitely want to upgrade your focuser. And there are many rack and pinion focusers too. So anyone that has gears like this one or this one, that's a rack and pinion focuser. And there's even focusers you can replace the focus knob on your Schmidt-Cassegrain that has a fine focus ability on it. But with a proper adapter, you can put a rack and pinion or Crayford focuser on the back of a Schmidt-Cassegrain too, lock your mirror in place, and then you don't have to worry about image shift and stuff like that. So there are certainly ways to upgrade and get away around the kind of drawbacks to some telescopes. All right, so real quick, even here with more accessories, I mentioned the Barlow lens. This was invented by the English mathematician and physicist Peter Barlow. So oftentimes I see Barlow with a lowercase b, but nope, it was named after a person. It's supposed to be a uppercase B, so take that. So Barlow lenses artificially extend the focal length of your telescope. They have like a negative lens in them. And so, if you look through them, it makes things look way far away than they really are. So Barlow lenses are cheaper than eyepieces, at least most of them are. And they're a way to give you more magnification for the eyepieces you have at a kind of a discount rate, as opposed to buying more eyepieces. So there are some pretty good Barlow lenses from Meade, Celestron, Orion, and Teleview out there. But Teleview has their power mates. They look exactly like Barlow lenses, but they're a bit different. Instead of a negative lens down here, they have a positive lens, and they do have some advantages over Barlow lenses, but I won't get into the specifics. I will refer you to the companion notes to this lecture. There are plenty of finder scopes out there. Quite often with lower end telescopes, they'll come with like a 5x32 finder scope, which is next to worthless, by the way. 6x30s are a little more respectable, but if you want to upgrade, you can get like a 7x50, 8x50, 9x50 finder scope. I usually tend to prefer the straight through designs, but I know a lot of people like ones with right angles, and that's fine. I personally, again, just prefer the straight through because you can just kind of, look above it and look right in, look above it, look right in to, adjust where you're pointing at. Well, you can't quite do that with when the eyepiece is off to the side. But for some Newtonians, this is a smarter, better way to go. But a lot of people just avoid finder scopes altogether and get yourself a one power finder. So there are lots of one power finders on the market today. And the first type, the red dot finder, we basically got from gun manufacturers. A lot of people bought these from gun manufacturers and put them on telescopes. So the telescope people said, hey, why don't we make our own and start selling them? So they did. So what these red dot finders do is they basically put a little red dot on the piece of plastic lens or glass screen there, and you do basically, just kind of look not close up, but kind of from a distance through the red dot finder, and put the red dot on the star or planet or in the general vicinity of the deep sky object you're looking for, and assuming it's aligned correctly, it should be there. So a lot better are Telrad finders. You have to be sure it fits on the telescope that you have. I know some Dobsonians it doesn't quite fit on, but Telrad finders are very popular one power finders. And again, like a red dot finder, Telrads don't magnify like finder scopes do, and they give you a nice bullseye sight. And in many planetarium programs like Starry Night or the Sky, you can put a Telrad sight to scale on charts you can print out or looking at your screen and stuff like that. So I mentioned previously in part 3 that this guy that has a website called skyspot.com, he sells these laminated flip charts meant for Telrads that I highly recommend. So you can purchase your Telrad and your Telrad sites from skyspot.com. There's a link to it in both the part 3 and the part 4 notes. So if you can't fit a Telrad on your telescope, like maybe it's a short Maksutov or just a Dobsonian where it doesn't work, you can also use a Rigel quick finder. The sight isn't exactly as nice as a Telrad, but again, they have a very short base and tall profile, so that makes it fit on most telescopes where a Telrad is just too long to fit. Now, if you do have a large aperture telescope, probably starting 6 inches and up, when you do look at the moon, it can be a little uncomfortable. And through a really large telescope, like 10 inches and over, if you look at the moon with no moon filter, you'll see it for the next like 10, 20 minutes, whether you're looking at it or not. So definitely get yourself a inch and a quarter or even 2-inch moon filter that threads onto the bottom or the barrel of your eyepiece. You can even get polarizing filters where you can adjust the darkness. And those are great for Jupiter, because Jupiter can be kind of glaring through really large aperture telescopes, or Venus. It just dies down their brightness a bit. Planetary filters are great. I have all the colors. And when I do get a chance to observe by myself and look at the planets, I tend to cycle through the planetary filters when I'm alone, but I don't do it with public viewing too much because nobody wants to see Jupiter in some funny color. But planetary filters are great at bringing out various details of Jupiter and Saturn, especially Mars, when it's near opposition. I won't go through what these specific colors can do, but I will refer you to the notes again about what various colored planetary filters can do. So they are really useful for planetary viewing if you do it, again, by yourself and have the time to study the subject at hand. And most are pretty affordable too. And then there are, of course, deep sky filters. And in today's era of light pollution, they're really mandatory. So there are broadband filters, known as kind of your general light pollution deep sky filter, that you can use when you're observing pretty much any deep sky object. There's narrowband filters like ultra high contrast, or sometimes they're just called narrowband filters, that are more specifically for emission nebulae or supernova remnants, like the Orion Nebula, the Lagoon Nebula, maybe the Veil Nebula. O3 filters, they are specifically for planetary nebulae, and hydrogen beta filters are for just really a handful of deep sky objects. I don't own one. I've tried them, and they really aren't useful for a lot. So they're not terribly common, but by all means, if you want, go ahead and try one. And obviously, you can get solar filters for your telescopes. Just remember, the solar filter goes over the front of the objective mirror, or the objective lens, or the primary mirror. And so solar observing can be a great joy during the day. So, maybe you're afraid of the dark. Then solar observing is right for you, right? That's a myth that solar astronomers are such because they're just afraid of the dark. So, but again, we're getting near solar maximum as we record this here today. So, yeah, definitely purchase a solar filter from Kendrick Astro, Thousand Oaks. Batter Planetarium, I believe, has them as well. Of course, they have the batter material that tends to give a white view, while Thousand Oaks makes the sun look a little more kind of yellow or orange. Kind of like this. So, of course, solar filters will be in high demand right now as we approach the April 8th, 2024 total solar eclipse. Or if you're not going to go to the path, you can at least observe the partial solar eclipse if you're in North America. Now, there are dedicated solar telescopes. They're all refractors, and they all allow you to observe the sun at a very specific wavelength of 656.28 nanometers, or if you're a real science geek, 6,562.8 angstroms. And that wavelength is known as hydrogen alpha. And it's a very specific part of the red end of the spectrum. And so hydrogen alpha telescopes from Lunt or Coronado, which is now owned by Orion, which was previously owned by Meade, but now Meade and Coronado are owned by Orion. They manufacture dedicated hydrogen alpha telescopes. There's also Daystar telescopes as well, but the ones I show here are from Coronado or from Lunt. There are filters available separately with the filter and the blocking filter, which is the diagonal, because these are not regular diagonals. They're also known as blocking filters in this case. You can't buy them for refractors. but I would just spend your money on a dedicated solar telescope, because if you sell your refractor like I did, it's very hard to find the adapters for the H-alpha filters you can adapt to different refractors. So it's just easier and quicker to get yourself a dedicated hydrogen alpha telescope. And they do have small 40 millimeters that are under $1,000. They're still pretty pricey, like $700-800. Bigger ones could be really much more expensive, but the hydrogen alpha sun is much more dynamic. I've got to see solar flares. I got to see one giant prominence one day fly away from the sun as part of a coronal mass ejection. You can watch prominences change in a matter of minutes or hours. It's just a really fun way to observe. And there are dedicated solar mounts now from Skywatcher called Solar Quest. These all have an 11-pound capacity. They have a built-in GPS. They auto-align and track the sun with a little sensor here that the standard go-to mount does not have. There is a little built-in 8-way joystick if you have to center the image a bit. And they have what's called a V-style or a Vixen mount. So they're meant for smaller refractors that can take a Vixen mount. Bigger refractors don't work like that too well. And they can be powered by batteries, but they do include a 12-volt adapter as well. Orion used to sell a version of these they got from Skywatcher. I tried buying the Orion version. It didn't work at all. And now I've noticed they've discontinued them because I'm guessing the ones they got were junk. But I've seen plenty of reviews from the ones from Skywatcher, and they do work. It's just the one I got from Orion didn't work at all. Okay, so let's get into dew. So basically, dew occurs when the actual air temperature falls to the dew point. So your telescope can get very wet very quickly. Telescopes like refractors are very susceptible to this, but all refractors usually have built-in or extendable dew shields. For a Schmidt-Cassegrain, you either have to buy one or build one. So here's a dew cap for your Schmidt-Cassegrain. Even Telrads have dew shields you can buy, but you can build one as well. But ultimately, what you're going to want to do, even for any telescope design, a refractor, reflector, or Schmidt-Cassegrain, is get yourself a dedicated dew prevention system. There are many dew controllers out there. I just show the one from AstroZap that can heat your dew heaters. Basically, they wrap around the front of the telescope, around the corrector plate or around the objective lens to just heat it just a little bit above the ambient air temperature to prevent dew from forming. And in Michigan, it's really the only way you're going to keep dew off your optics the entire night. Even with the dew shield in Michigan, that just buys you a couple hours sometimes. And they even have them for secondary mirrors, because I really needed one of these for my 8-inch f4 Newtonian, because the secondary mirror kept dewing up, and that dews up a lot faster than the primary. And these are meant to get rid of frost on like the inside of your windshield, but you can even use them out in the field to remove dew if you don't take any of the preventive measures. All right, so I apologize for going a little long here, but I recently added again a new addition to part 4 here, because over the past several years, electronically assisted astronomy has become much more prevalent in the world of amateur astronomy. So electronically assisted astronomy, or EAA, is the use of a technological aid for astronomical viewing. You can use light intensifiers like night vision optics. Teleview sells a night vision scope that they can attach to their eyepieces, and I've used one of those, and they are very impressive, but $4,000 or so is a little too rich for me. So you can do that form of EAA with a night vision scope hooked up to your eyepiece, but you can also use video cameras like a Melon Cam. I've never seen one of those. I don't know much about them. I did purchase a Revolution Imager, but never used it, and frankly need to sell it. But that's a great cheap way to do EAA. out in the field, either by yourself or with the public. But what most people do is they use either their CCD or, of course, now a CMOS camera, because as we'll talk about next time, CCDs are becoming more extinct. So you can adapt any telescope to a one for EAA by the use of one of these methods. But what a lot of people are now doing is they're purchasing dedicated smart telescopes, specifically designed from the ground up for EAA. And we'll talk about those in more detail here shortly. So, of course, the purpose of EAA is to view targets near real time by taking short exposures in a short time period. And EAA is a form of astrophotography, but the goal of astrophotography is usually to take a bit longer time exposures, maybe up to 5 minutes to even 30 minutes, while with EAA, you're usually under a minute or less. So you take a whole bunch of short exposures, while a app on your phone might combine them and stack them and improve the image over time. So it's used to see, more than you might if you were observing through an eyepiece. And you'll notice here often with EAA, I will say you are viewing targets. You're not observing them. Observing means, to me, you use your eye, because if your goal is to see the stuff for yourself, then you don't want to use EAA. But there are plenty of applications where EAA is maybe the way to go for you. But just remember, you're not actually observing this stuff. You're not really seeing it. You're just seeing kind of real-time images of it. So why do use EAA? It does increase observable detail. You probably will see more detail and even short images of galaxies than you will through the eyepiece of most telescopes, unless you have a big telescope at a very dark site. If you do have vision problems like glaucoma or severe astigmatism, you might prefer to use EAA. It is a lot better way to go in heavily light polluted skies, because with EAA you can use special filters for imaging to bring out more detail in light polluted skies. You can view in comfort. I've seen promotional images where the people are inside watching a big screen TV, which, I don't know, for me that takes a lot of the joy out of being outside in the elements. But you can see, like with the image here, at least they're outside, looking at their smartphones. That's, still not observing stuff in the night sky, through a telescope, but still, it's still, if you're handicapped or just can't bend down to look through your eyepiece anymore, EAA is a great way to go, because you can observe sitting down. And really, large apertures are not required. In fact, most smart telescopes do not really come in large apertures. They're all pretty limited to smaller sizes right now. And you don't need nearly as much equipment as you do with astrophotography. For mounts, you can use a German equatorial mount on your standard telescope, but pretty much all smart telescopes are the all-azimuth design. You can even put a telescope on a good capacity star tracker. We'll talk more about those next time as well. And pretty much all smart telescopes are go-to. So they automatically point to the target that you want, like lots of telescope mounts can do. Pretty much any telescope will do. Pretty much all smart telescopes today are either refractors or Newtonian reflectors, or there's one case where it's a special kind of reflector that we'll see here shortly. And they're all pretty short focal length, and again, small in aperture. The cameras can again be video, CMOS, or DSLR or mirrorless cameras. They do not necessarily need to be cooled, but of course cooling improves the sensitivity of the imaging chip, and it reduces noise as well. But most smart telescopes do not have cooled cameras. If you want to see detail on Venus, you can put on an ultraviolet filter, because you need an ultraviolet filter to see the details and clouds on Venus. You might even be able to observe in the near infrared. And you can also, of course, see deep sky objects in color. if you have a color camera, of course. Not so much if you use the night vision approach, but pretty much all smart telescopes, maybe a handful don't, have color sensors that give you color images. And of course, if you want to document your images, all you have to do is save them, and you can include them in your observer's log, or at least your viewer's log. And again, they are great for small groups and public outreach. Would I want an entire observing field of smart telescopes at my public observing sessions? No, but it is nice to have some of them there. It's just a different approach, and there's nothing wrong with that. I guess you could say I'm an observing purist. I'm also an astrophotographer, but if this is the way you like to go, there's absolutely nothing wrong with it. Some people turn their nose up at EAA because, yeah, as I said, you are not actually seeing the objects, but it is a great way to get outside. Don't sit inside in your living room and watch these on your big screen TV, unless it's the dead of winter and it's really cold out there. So here are some of the smart telescopes that came along. Again, there's a little more detail in the notes on these, but the first type of smart telescope was the unistellar. They have the Equinox 2. That's a 4.5 inch with a 450 millimeter focal length. It does have a 6.2 megapixel sensor, which is pretty respectable compared to most smart telescopes. There's the Odyssey and the Odyssey Pro. The Odysseys are both 85 millimeters. They have a 320 millimeter focal length and just a 3.4 megapixel sensor, which is a little on the low end for me. The Pro does have a 4.1 megapixel though, and that electronic eyepiece that Unistellar is known for. You'll get a better view of it here. So this is like a little computer screen, like a little screen that acts like an eyepiece. It's not like an actual live view of the telescope or the target you're looking at, but it's pretty close. So there's the Odyssey Pro. And the EV Scope was the first one, but now they have the EV Scope 2. And again, the prices vary from $2,500 for the first two, $4,000 for the Pro, and this one's about $4,900. So, smart telescopes are not cheap. And again, this one has a 4.5 inch aperture with a 450 millimeter focal length. There's also ones from another French company called Vaonis. They have this really unusual looking one called the Hestia. This does not have an imaging sensor, but what you do is you put your smartphone on top of this this ocular on the top, and your smartphone acts as the imaging sensor. So in a way, this could potentially be the largest megapixel sensor if you have a high sensor on your smartphone. So as far as I know, I didn't do a whole lot of research on these, but these don't track. So they're mainly for brighter targets like the moon and the sun. They even market one of these for the upcoming eclipse. So these are only $300, but they only have like a 30 millimeter aperture lens, and they give a 25 power magnification. Then there's the Vesperia and Vesperia Pro. They're both 50 millimeters. The regular version has a 200 millimeter focal length, while the Pro has a 250 millimeter focal length, and they both have, I believe, an 8 megapixel sensor. Here's the Pro version shut, so you can see they're pretty compact when they're closed. That's one of the joys of smart telescopes, is they're pretty portable. And then here's the Stellina. So this one cost about $4,000. The Vesperia, by the way, they're about $1,500 and $2,500 respectively. So the Stellina is about $4,000. They are expensive. This is an 80 millimeter refractor with a 400 millimeter focal length and a 6.4 megapixel sensor. But here it is in the extreme. This is the Hyperia. This one has a 6-inch aperture lens, 1050 millimeter focal length, but it has a 61 megapixel full frame sensor. So this one has a big modern chip in it but it weighs 165 pounds and it costs $45,000. So if you do have another one of these lying around not doing anything, yeah, go ahead and send it to me. And then Dwarf Lab has the Dwarf Lab 2. These are really affordable. There's the standard version for $459 or the deluxe version for $595 that comes with more filters and more accessories like an extra battery. So they're only 24 millimeters in aperture. But the two lenses, one's a wide field, one's a telephoto lens. And so the telephoto lens gives a 3-degree field of view, if you call that telephoto, while the wide field version gives a 50-degree field of view. So that'll give good views of like all the nebulosity in Orion at the same time. So now we're getting a little more affordable here, and that includes the ZWO C-Star 50. This one's only $500. It has a 50 millimeter aperture, 250 millimeter focal length, and a 2.1 megapixel sensor. So it's a pretty small sensor, but that's why it's so affordable. And it's, again, it's just a very portable setup that you can quickly take out and, you know, just grab a few quick views of deep sky objects in the sky. But here's the very newest one on the market, the Celestron Origin. I don't even believe they've even shipped yet. This one costs about $4,000, but this uses a 6-inch version of Celestron's popular Rowe-Ackermann-Schmidt astrograph. It's a kind of catadioptric telescope, and astrograph means it's specifically meant only for astrophotography. And this one uses a 6.44 megapixel sensor. And it weighs about 42 pounds. So it's not quite as portable as some of the other smart telescopes, but still not severely limiting like that $45,000 thing, that monstrosity. I can't imagine anyone actually buying that, but I'm sure some people would. Apologies if you did, but geez, that's expensive. So this is a really nice one. I mean, this is an excellent imaging telescope. The one thing I'm not really sure about, at least in this case, I'm sure it's not true for any of the others, is if the camera is upgradable. It kind of looks like it is from some of the pictures, but two big improvements these telescopes need. They need to come with better sensors, but not be much more expensive. And maybe in future designs, I believe some of them have it now, would be field derotators. Because the big professional telescopes, they aren't mounted on German equatorial mounts. They are mounted at alt-azimuth styles, but to avoid trailing of stars or little star step stars, the camera slowly rotates as the telescope tracks. So some of the higher end ones, I do believe, come with field derotators where you can do longer exposures. But usually the whole point of EAA is to do a whole bunch of really short, like 20, 30-second exposures and live stack them over time. So there's going to be a lot more of these type of telescopes coming out in the years ahead, and I'll do my best to keep up with them. But there are quite a few already. So just real quick, one thing that's important for me when I observe through a telescope is to understand what I'm seeing. I like to know a little bit of history about the deep sky objects that I'm looking at. And I like to know a little bit about the science behind them. So that's what a lot of these books do. So I highly recommend all these books here. The Deep Sky Companion series by Stephen James O'Meara, legendary visual observer. He also came out with the Herschel 400 Observing Guide. I believe there are more volumes of the Annals of the Deep Sky now. I forgot to update this, but there's going to be a lot of volumes of this thing in the years ahead. I don't know how many, but these really get into the nitty science of many of these deep sky objects that are popular. And then the Night Sky Observer's Guide gives lots of observing notes of what these things look like through various aperture telescopes. At least one of these may be out of print, but I believe they're all still available and published out there. But finally, the last thing I want to mention is don't let any really geeks in the hobby influence you, because there are some people that really like purchasing more of the equipment than they do observe, because I've seen guys on Astromart, for example, with just hundreds and hundreds of ratings, which means they sell and buy hundreds and hundreds of items. And, so some people are in it for the equipment, and they are equipment geeks. They got to have the newest, the best equipment, and they will tell you, no, you shouldn't have this. You should buy this newer, better thing. But just remember, the absolute best telescope is the one you use most often. It may not be the largest aperture. It may not be the best optics. It may not have the best mount. But if it's one you actually take outside and use on a clear night, it is the best one for you. So above all else, keep that in mind.